All right, good morning, everybody. Happy Thursday. Welcome back to the long coffee break. This week, we have the privilege of being joined by Dave Binns, the Director of Engineering at Cambridge Air Solutions. And our topic this week is high temperature heating and ventilation. What is it and why does it matter? So really appreciate your time. Thank you to everybody for joining us. Don't forget to stay to the end. We will have a giveaway winner again this week. So stay tuned. And with that, I'm going to turn it over to Dave.
Hey, thanks, Jason. Thank you all for being here. And again, what the technology we're talking about today is HDHV, or like we said, high temperature heating and ventilation. And so first and foremost, what is it? HDHV are direct fire industrial heaters that utilize outside air with a high temperature, meaning they have a greater than 150 degree discharge and a greater than 140 degree temp rise. And then the heating and ventilation aspect of the technology means that this technology can be used to not only ventilate the space to meet your ventilation requirements, but also it has fully modulating controls to meet our space heating requirements as well. For those that are in the industrial warehousing or industrial heating space or seen these before, probably know HDHV very well. For those that have not maybe worked on large distribution projects, have not. So let's talk about the history of HDHV and where did it get started? And ultimately, HDHV was really introduced into the market back in the 90s by Cambridge, when we were able to achieve that high temperature, high discharge temperature cleanly, effectively, and reliably. And what that technology did is it transformed the large warehouse and distribution space. And how to transform that space is it really changed the way that design build contractors, end users, and engineers design these spaces. And what happened in the mid 90s, that early adopter design build contractors saw that they could lower their installation costs by over 40%. They could take buildings that were typically using 30 or 40 unit heaters and reduce the number of units to 6 to 8 units. They could reduce their piping costs, their gas piping, their electrical, their installation costs, and they were winning more projects. Simultaneously, what happened was end users saw their energy bills cut in half. They saw that they were not only costing them less from an install cost perspective, but also their operating costs were having demonstrable savings. And thirdly, which really is not, I think, it's becoming even more of a forefront today, is that these buildings typically did not have mechanical ventilation before. So this technology is primarily meeting the heating requirements, but building tenants and the people inside the space saw their indoor air quality improve because we were actually ventilating spaces before that was using primarily recirculation technologies. So what those three benefits did is it changed the way that we design large warehouses today.
So Dave, how is this similar or different from what we might think of as a traditional makeup air unit?
Yeah, a great question. There are some really, I would say, broad similarities, but a few distinct differences which equate to really the performance and the energy savings differences. So if we think about what HDHV is, we probably are maybe more familiar with a typical draw-through direct-fired makeup air unit. And when I say a makeup air unit, these are typically higher CFM, lower delta Ts, where I'm drawing the air across the burner. Because my mechanical components are in the hot airstream, I'm typically limited to discharge temperature because bearings, motors, belts, and pulleys don't really like to be in these extreme temperatures. But they both have 100% outside air. They're both 100% combustion efficiencies. They both have no heat exchangers, and they both have no flue losses. But what HDHV does is by moving the blower upstream of the burner, where my mechanical components are now in the cold airstream, if I can get my burner to be cleanly, effectively, and reliably burn at the high temperature, I can now put more heat into a smaller box, and that has demonstrative savings from an energy perspective and an installation cost perspective. So for those that aren't familiar with that, they may ask themselves, well, if I have not seen a direct fired unit, how is this safe? And how can it be safe for me to deliver the process combustion into the space? And I want to actually say that these technologies are actually inherently safer than recirculated indirect fired heat exchangers. And so when we talk about safety of really any combustion device, it really comes down to carbon monoxide poisoning, right? So the CDC did a study a few years ago. What they found was that every year, about 15,000 emergency room visits are the cause of carbon monoxide poisoning. And in those cases, about 2/3 are caused by automobile exhaust, and 1/3 are actually caused by indirect fired heating systems, indirect fired home heating systems. And inside that study, there has been 0 exposures caused by a direct fired 100% outside air system. And you may ask yourself, why? how can a technology that's designed to deliver the process of combustion actually be inherently safer than an indirect fired system? And it ultimately comes down to what is the root cause of these CEO exposures. And in all cases, the single root cause is lack of adequate ventilation. Whenever we have recirculating technology, really any indoor air pollutant, ventilation is the safety device. Dilution is a solution to pollution. And what this technology has and why it makes it inherently safe is that I cannot separate the combustion airstream from the ventilation airstream. I am always ventilating as long as I am heating. So I already have extremely low discharge of any kind of CO or byproduct combustion, but I'm always ventilating and I'm always diluting those products, which is why direct fired 100% outside air systems are actually inherently safer than recirculating indirect fired systems.
Dave, let's talk a little bit about efficiency and energy costs. Earlier, you said that we can increase ventilation while decreasing energy costs, which seems a little counterintuitive. Can you walk us through that?
Yeah, you're exactly right. If your first thought, if new technology, your first thought was, how are we not killing people left and right? Your second thought is, how in the world can you save energy versus a recirculation technology? How can it be energy efficient to deliver outside air to the space? How can I lower my energy bills by utilizing outside air? Well, as engineers, we know that every building must have ventilation if it's designed for human occupancy, right? So we have this beautiful standard ASHE 62.1, which gives our engineering community guidelines to help make sure that their indoor air quality is good and safe. Secondly, this air must come through either through natural infiltration or mechanical ventilation. And sometimes in large warehouses, large distribution centers, there can be a balance of ventilation and infiltration. And when we look at those two key components, that's what makes up the total air load of our building. So if you think about it, how can it be energy efficient to utilize outside air? The first thing is that every building gets outside air and we have to heat it somehow. So let's look at the most energy efficient way to heat our ventilation requirement. So let's take an example of a building. If we have a building that has a 10,000 CFM exhaust and we take our 0-degree outdoor ambient condition, and I've got to heat that up to 7 degrees or whatever my indoor design temperature is, with a direct fire 100% outside air system with no heat exchanger and no flue losses, I have the most combustion efficient technology available to heat my ventilation. So if I'm looking at the most energy efficient way to heat the air load, it's going to be utilizing 100% outside air direct fired unit. This is why 95% of all kitchen systems utilize this exact technology. Low cost, fairly simple system, high reliability, and extremely energy efficiency because it's got to run all the time to meet my ventilation loads. Now, the second thing that we have in large warehouses and building is it's not just the ventilation load. What about my conductive load? How do we heat the skin losses or those conductive loads from that cold outside and warm inside? Well, what HDHV does and why it's energy efficient to utilize outside air is that if I can turn my discharge temperature up to a high enough temperature where I have this extra heat available to counteract my skin losses, then I can not only cover my air load, but also my conductive loads with the same device and with the same burner technology, which is 100% combustion efficient, 100% efficient. So this is really all the sort of magic sauce to HDHV is I take a ventilation only device, but if I can dial the discharge temperature up to as high as I can and get enough extra heat to counteract all my skin losses, with one device, I can meet my ventilation requirements and I can meet my conductive loads, and I can do it with the most energy efficient way to combust gas and to heat. And so what we do is we take a 10,000 CFM normal ventilation makeup air unit. By dialing up to 160, I now have an additional 1.1 million BTUs of heat available to heat skin losses. So why is 160 important? Because if I have that 1.1 million BTU conductive load, only the available heat above space temperature can counteract that skin load. So if I, for instance, were using a low temp draw through unit and I was limited at 120 degrees, I would need 24,000 CFM to meet that skin loss. So the problem that we see when they try to utilize low temp makeup air units or even 100 degrees makeup air units to compare to an HDHV, they end up putting more CFM, more BTUs, more energy, and a lot of wasted costs.
So Dave, typically we don't see discharge air temps nearly this high when we look at most other solutions or types of equipment applications for heating. Are there any concerns we should be aware of with respect to code requirements or stratification?
Yeah, there's no restrictions from a code requirement. These technologies are all zero clearance to combustibles. And really what allows us to meet kind of those two key concerns is our high velocity, right? So yes, we are discharging 160 degrees at the space, but which can create quite a buoyant effect if you don't have destratification technologies. In many large warehouses, they use pair fans, zoo fans, HVLS fans. But what our HDHV technology we use high velocity, and we actually induce a large air turnover or air mixture of that kind of warm, stagnant air to the ceiling and help mix and push that down to the floor. So with a very small CFM, I can get large air movement and I can get good air mixing. So if I mix 10 parts room air with 1 part 160 high velocity air, I can now, by the time it hits the floor, it's a much more average temperature of maybe 75, 85 degrees, and I get good air mix and destratification without needing to add a lot of other ductwork or recirculation fans, all inside that same device.
I just want to take a minute to highlight here the fact that Cambridge has a very robust engineering team in-house, and they have the ability to work with us to help us mock up any schematic design concepts. So if you have any projects coming up in the future where this could be a good fit, don't hesitate to reach out to your long sales engineer, and they can help you work with Cambridge to get some clarity on heat loads and airflow requirements, and even space layouts, how many heaters we might want to put in the space and how far to space them apart, all that good stuff. Then this just shows you real quick that we have tremendous flexibility when it comes to airflow configurations and arrangements. We can do outdoor, indoor units, vertical or horizontal configurations.
Yeah. Thanks, Jason. And I'll just leave you with one last example. We talked a little about the technology, some of the theory, what is it? Well, how about some real world examples? I'll just share this as one of our building studies of a really extensive building study program we have of over 400 different types of buildings, usage, or even areas in the country. But this really shows you how the proof is in the pudding. These are 2 large distribution centers for a client. They're exact same building, exact same construction, just happen to be in different locations. And one building decided to use a lower temperized draw-through makeup air unit. The other building utilized the high temperized blow-through HDHV technology. Both had 100% outside air. Both had 100% combustion efficiency devices. But that simple fact of having high temperized, high velocity, and blow-through equated to massive energy changes. The building that utilized the Cambridge system saved about $177,000 a year in electrical and gas costs. So whenever we hear a draw-through makeup air is just like a blow-through HDHV, there is massive energy costs and savings to our end users. When this customer found this out, they quickly, a few years later, took off those fairly new draw-through makeup air units, put in a blow-through, and have been saving tremendous amounts of gas and electrical bills over the years.
Thank you very much, Dave. Really appreciate it. Again, my name is Jason Long. I'm a sales engineer with Long Building Technologies. I want to say thank you to everyone for joining us this week. We really appreciate your time. We know everybody's busy, so we're grateful for you making the commitment here. Next week's topic will be maximizing your energy profile with evaporative cooling technologies. Travis Cowan from Long will be leading that along with Peak Plus. Thank you again to everyone. We hope you have a great rest of your Thursday and a good week. We'll look forward to seeing you next Thursday. Thanks.